So today we will be doing refrigeration. So the first part here will be the introduction to refrigeration cycle. So first thing is you have to know what it means by refrigeration. So here, the term refrigeration means cooling a space, cooling a substance, or cooling a substance or a system to lower temperature. Other than to lower temperature, it also has to maintain. It has to maintain the temperature, okay, of the substance or the system, okay, below the ambient temperature. So when any food or anything that you put into a refrigerator that is subjected to fluctuation in temperature, it will cause the food to contaminate or spoil much faster. Okay, so other than to keep it at lower temperature, the temperature also must be maintained constant throughout. Okay, so while the remove of heat, okay, is rejected at higher temperature. So you have a continuous change of phase of the substance from liquid to vapor or from vapor back to liquid, so the temperature can be maintained constant. So as we know, okay, during change in phase of a substance, there shouldn't be any changes in temperature. Or when there is a change in temperature of substance, there shouldn't be any change in phase. Okay, so if to keep the temperature constant, the way that we can do is to allow it to change completely from liquid to vapor while it is in the cooling compartment. Now, second point, refrigeration is artificial or it is human-made cooling. Energy in the form of heat is removed from a low temperature reservoir, just like your freezing compartment, and transferred to a higher temperature reservoir. Usually is transferred to the condenser or from the condenser to the surrounding air, Fourth point, work of energy transfer is traditionally driven by mechanical means. So usually this is being performed by a compressor, a refrigerant compressor. Okay, so then refrigeration has many applications, including household refrigerators, industrial freezers, and air conditioning system. Now, heat pumps may be used, okay, may use the heat output. Heat pump may use the heat output of the refrigeration process and also may be designed to be reversible, but are otherwise similar to air conditioning units. So we will be discussing about heat pumps later on. Okay. Now, thermodynamics heat pump cycles or refrigeration cycles are the conceptual and mathematical models for heat pump, air conditioning, and refrigeration systems. Now, a heat pump is a mechanical system that allows for the transmission of heat from one location, the source, at a lower temperature to another location that is called the sink or the heat sink at a higher temperature. Thus, a heat pump may be thought of as a heater, if the objective is to warm the surroundings. Okay, if the objective is to warm the surroundings, and usually is called a heater. Okay, so usually it's being used in colder countries. Now, a refrigerator or cooler, heat pump is a heater, okay? And refrigerator can also be called a cooler. Its objective is to cool the heat source or to cool whatever that is placed inside a compartment, okay? In either case, the operating principles are close. That means between the heater and the cooler, the operating principles, they are very close to each other. Okay? So heat is removed from a cold space or a cold place to a warm place. That is refrigerator or cooler. Okay? Heat pump or heater is to heat up a space. Refrigerator or cooler is to cool down a space. Okay, so that's for the first part, the theoretical part of refrigeration. So we'll continue with the principal parts of a refrigeration cycle. So there are a few components within the refrigeration cycle which we have to take note. So the principal parts are, the first one is an evaporator, which is a heat exchanger, So inside the evaporator, usually you have liquid refrigerant running inside tubes or coils. Okay, you have cooling agent or the refrigerant is running inside of tubes or coils. Okay, so as it runs through the tubes or the coils, it will try to absorb, it will tend to absorb heat from the surrounding when the air particles within the compartment is being trapped or it is being in contact with the tubes, which inside you have refrigerant. That means cooling agents. Okay, those are the substances which operates at lower temperature. We usually call them as refrigerants. Now, evaporators, usually they are made up of tubes, coils, and fins. Okay, so whose function is to provide a heat transfer surface. Usually when you refer to your household refrigerator, the freezing compartment section or the part, that is where your evaporator is. Okay, its function is to provide a heat transfer surface. And remember, within or beneath or underneath of that surface, you have tubes running over a coil. And inside the coil or the tubes, you have refrigerant. Liquid refrigerant will be changing to vapor refrigerant as it absorbs heat continuously from its surroundings. Okay, through which heat can pass from the refrigerated space or product into the vaporizing refrigerant. So the refrigerant that is running inside the tube or the coil will vaporize as it absorbs heat. Okay, because these refrigerants, they are very sensitive to heat energy. The moment even a slight amount of heat energy flows to it, it will start to vaporize in the evaporator. Okay, evaporator usually is the freezing compartment of a household refrigerator. Suction line, which conveys the low pressure vapor from the evaporator to the suction inlet of the compressor. So suction line directs the vapor refrigerant to the compressor suction inlet. That is the purpose of the suction line. Then the vapor compressor. Now why we call it as vapor compressor? Because this compressor here, only deals with vapor, not liquid. Compressors here cannot deal with the mixture of vapor and liquid because it will burn. Okay, so in case if there is an overflow of liquid refrigerants into the compressor, it will cause the compressor to burn easily. So it is only dealing with vapor refrigerant, whose function is to remove the vapor from the evaporator and then to raise its temperature and pressure. That means to raise the pressure and temperature of the refrigerant or the cooling agent, okay, to a point such that the vapor can be condensed, okay, condensed with normally available condensing medium. So this refrigerant, which is being delivered to the compressor, the pressure and the temperature will be raised. And then after that, it will be sent to the condenser for condensation processes. Okay. Now, discharge line that refers to the compressor. So the compressor has a suction line and a discharge line as well, which delivers the high pressure, high temperature vapor from the discharge of the compressor to the condenser. And the fifth part or the fifth component is the condenser. The condenser looks similar like an evaporator. But then when you refer to your household refrigerator or those conventional refrigerators, you usually can see black coils or black tubes that is placed behind the refrigerator. Okay, so that black surfaces usually is what we call the condenser. So the refrigerant that came out from the compressor will goes into these tiny little cubes, okay, which we call condenser, where heat is being rejected to the surroundings. So the temperature difference between the surroundings, that means if let's say your refrigerator is placed inside the kitchen, the temperature difference must be large enough to enable the rate of heat transfer to be high. So the cooling of the refrigerant in the condenser will happen faster. Okay, whose purpose is to provide a heat transfer surface, both to provide heat transfer surface, okay, through which heat passes from the hot refrigerant vapor to the condensing medium. So usually, if let's say, for example, you are using water-cooled condenser, so the heat from the vapor refrigerant that is running inside the condensing tube will be rejected, or the heat will be transferred to the water that is coming into contact with the tube, okay, by conduction and convection. Okay, so that is water cooled. You have air cooled, you have water cooled, and other means. Okay, receiver tank, which provides a storage for the condensed liquid, so that a constant supply of liquid is available to the evaporator as needed. Okay, then refrigerant flow control valves, regardless of type. The function of any refrigerant flow control is twofold, two functions. One is to meter the liquid refrigerant from the liquid line into the evaporator at a rate commensurate with the rate at which vaporization of liquid is occurring. So how much of liquid refrigerant is being vaporized, how much of liquid refrigerant will be allowed to go into the evaporator. That is to meter, that is why I say to meter the liquid refrigerant flowing into the evaporator. Second point, to maintain a pressure differential between high and low pressure sides of the system in order to permit the refrigerant to vaporize under desired low pressure in the evaporator, while at the same time condensing at a high pressure in the condenser. So these are the two functions of a refrigerant flow control. Usually is what we call a thermal expansion valve. Okay, so that is operated by means of temperature difference. Okay, and then the next and the last, that is the refrigerant, that is the cooling agent. Now, is any body or substance that acts as a cooling agent by absorbing heat from another body or substance to be suitable for use as a refrigerant in the vapor compression cycle. A fluid should possess certain chemical, physical, and thermodynamics properties that make it both safe and economical. Okay, this is the 2 points, the most important point. One is safe and must be economical. Now, it must not be toxic, that is another point, which will cause suffocation if high concentration, and easily detected in the case of leakage. So in case of any leakage, so it must be easily detected. Otherwise, in some cases, let's say in some refrigeration plants, they might use ammonia. So if high concentration of ammonia, it will cause those people who are operating the system, okay, die of suffocation. Now, it must not be explosive. That is another point. It can't explode easily, and it cannot be flammable. That means easily burnt. Cannot be easily burnt and cannot easily explode. Those are the points that is relatively or very important when you do the selection of refrigerant. Okay, so in the later part, I will show you a few types of refrigerants and their usage and why some of them are being banned. Okay, so and also must not any effect to the ozone layer, such as those CFCs, that means chlorofluoro, okay, chlorofluorocarbons refrigerants cannot be used, okay, because it will give an effect to the ozone layer and it causes global warming effect. So these are the few important parts in refrigeration cycle. So these are the two theory parts, okay, before we start with reverse Carnot cycle or with problem solving. So this will give you a general idea how a refrigeration cycle works. And for the time being, okay, thank you very much for being here and listening to my explanation. Thank you. Now we will be into reverse Carnot cycle. Now previously we had done Carnot cycle, and this is called reverse Carnot cycle. This is where initially refrigeration cycle is being adapted. Okay, so starting from reverse Carnot cycle. So from a reverse Carnot cycle, okay, the heat flows in the direction of decreasing temperature. Okay, usually heat flows, okay, based on normal practice. Heat flows is actually flowing from high temperature to low temperature. So that is why it says it flows in the direction of decreasing temperature. So it flows from high temperature region to lower temperature regions. Now the transfer of heat from a low temperature to high temperature, that means opposite, then it will requires what we call refrigerator or heat pump. So in refrigeration cycle, actually the heat flows from low temperature region to higher temperature region. It's different from what we have studied in heat engines, where heat flows from high temperature region to lower temperature region. So if let's say in this case, if we want the heat flow from lower temperature region to higher temperature region, so we need or require something which we call a compressor. A compressor will do the job in raising up the pressure and to circulate the refrigerant. So refrigerators and heat pumps are essentially the same device. They only differ in their objectives. Okay? So the performance of refrigerators and heat pumps is expressed in terms of coefficient of performance. We don't call it as efficiency. We don't call it as an efficiency. We call it as a coefficient of performance. Okay? COP instead of efficiency. And the definition of COP is the same as the definition of efficiency. That is desired output over the required input. So COP in short means the coefficient of performance. We have coefficient of performance for heat pump. Remember, heat pump and refrigerator is actually the same device. Okay, so it depends on its desired output. If the desired output is to heat up the environment, or the desired output is to heat up a space, okay, or an empty space or a room, then it requires a heat pump. Now, if let's say, for example, the desired output is, let's say, to cool down, okay, the space or to cool down an area, so that would be the refrigeration. That would be the refrigeration. So you have COP for heat pump, and the COPR stands for refrigerators. So the coefficient, the coefficient of performance for refrigerator. So this is your reverse Carnot cycle. As you can see, heat flows from the refrigerated space or the low temperature region to the higher temperature region, that is the condenser. Okay, so here you would have the evaporator, the refrigerated space, and here you will have the condenser with the surrounding air. So heat is being absorbed, or heat is being taken by the refrigerant by means of circulating air. So the air which is circulating within the compartment of the refrigerator, I'm taking refrigerator as an example. Okay, the heat that is circulated by the air will be picked up by the refrigerant, liquid refrigerant that is running inside the tubes of the evaporator. Evaporator is made up of plate, tubes, and coils. Okay, so you have heat absorption. During heat absorption, you will have a decrease in entropy and also a change in phase of the substance from liquid to vapor. Heat absorption usually is called the refrigerating effect or the cooling effect. So in order to transfer the heat, from this low temperature region to this high temperature region, it requires this energy here, which we call the work input. Usually is performed by the compressor, the refrigerant compressor. So the refrigerant compressor purpose is to circulate the refrigerant and also to raise the pressure and temperature of the refrigerant so that it will be able to be rejected to the surrounding air in the condenser. So this would be your heat rejection. This will be your heat absorption, or usually most of the time we call it as refrigerating effect or cooling effect. This would be work input from the compressor. So it works in a reverse direction compared to the heat engine. Heat engines goes in clockwise direction, and the refrigeration cycle will goes in the anti-clockwise direction, which I've shown you in this diagram here. Okay, so that is work input, and this is heat absorption, and this would be your heat rejected. So you have energy input from these two streams. One is work in, and the other one is heat absorbed. So going in, and this as the energy that is going out, which is the heat rejection. So by energy balance, you can say this plus this, both are in, and this is out. So this plus this must be equal to this, okay, according to the energy balance. So this would be a TS diagram for a reverse Carnot cycle. It looks almost similar to what we have for vapor Carnot cycle. That is a steam power plant, okay, and the only thing difference is this is in anti-clockwise direction, and the previous heat engine is in clockwise direction. So you can see, okay, everything is working in the reverse direction from low temperature to high temperature. Heat engines is from high temperature region to low temperature region. Okay, so as you can see, it consists also two isothermal process and two isentropic process. The higher pressure line is called the condenser pressure, and the lower pressure line is called the evaporator pressure. So remember, when you look into this diagram here, now 0.2 is dry saturated, 0.3 saturated liquid, wet vapor, and wet vapor refrigerant. Okay, so 1 to 2 and 3 to 4 is reversible isentropic, 2 to 3 and 4 to 1, they are reversible constant pressure and isothermal. Okay, so 1 to 2 and 3 to 4, 1 to 2 is isentropic compression, 3 to 4 is isentropic expansion, 4 to 1 is constant pressure heat absorption or refrigerating effect, and 2 to 3 here is constant pressure or isothermal heat rejection. Okay, so based on that, okay, in plus in, that means work in plus RE should be equals to the heat rejected. Okay, so remember COP HP refers to the coefficient of performance of heat pump. COPR is the coefficient of performance of the refrigerator. So we know that area of TS diagram is the heat flow or the heat energy flow. Okay, so here you can see in the first TS diagram, you can see 2 to 3, this is a decrease in entropy. So the system will undergo, or heat will be transferred out from the system. Our system here is the refrigerant, is the cooling agent. So heat is rejected, okay, to the surrounding when it flows from state point 2 to 3, where it undergoes constant temperature or constant pressure heat rejection. And you can see that the entropy is decreasing. That means it shows that the heat energy content within the system is being transferred out from the system. Okay, then the next TS diagram here, you can see state point 4 to 1, and this area here again represents heat flow. So 4 to 1 shows you an increase in entropy. So that means there is a heat flowing into the system or to the refrigerant. So that is considered as the heat absorption, the heat that is being absorbed by the food, by the substance or whatsoever you put inside the refrigerator, which contain a certain amount of heat. So the heat will be transferred to the refrigerant that is running inside the evaporator tube. So that is why you can see the entropy increases, and that is represented by this area here. So the area of this represents the heat One is heat rejected, so that is the height multiplied by the base. And this one also the same, the height multiplied by the base. So heat absorption, most of the time we call it as refrigerating effect. So RE is the short form for refrigerating effect or the cooling effect, or you can use RE instead of Q absorb. So RE, or the refrigerating effect, usually is equivalent to the area that is within or below the process path of 4:1 of a TS diagram. So this area here, whenever you see there is an increase in entropy, that will be refrigerating effect. Don't confuse with this. Okay, the refrigerating effect, okay, shows at the lower part of the TS diagram. And it also shows you the increase in entropy because the refrigerant is actually taking in heat energy from the surrounding. So that is why the entropy increases. And also because it is changing from liquid to vapor, you got to know that heat is being absorbed by the liquid refrigerant in order to change to vapor refrigerant. So COP is also defined as desired output over required input. So as I have said, efficiency and COP definition are the same. Efficiency, usually we measure something that is below 100% or equals to 100% or 1. Whereas COP is when you have something that is higher than 100% or higher than 1. So that is why we don't use the term efficiency for refrigeration cycles. We use a term which we call coefficient of performance, and is defined as desired output over required input. So it depends on the refrigeration cycle. You are looking at the heater part, that means the heat pump part, or the cooling part, that is the refrigerator part. So if you are looking at the heater or the heat pump part, then you will have COP/HP. So the desired output will be this: heat rejected to the surrounding. You are rejecting heat to the surrounding. So the desired output would be this for heat pump. The required input is the same, that is pressure work input. If you are referring to the refrigerator, then the desired output would be this. That is 4:1. Okay, so the desired output here is to cool down the surroundings. This one is to heat up the surroundings, because here they are rejecting heat to the surroundings. Here they absorb heat from the surroundings. So this part is for cooling and this part is for heating. So COP/HP refers to this as desired output, and COPR refers to this as its desired output. So if COP/HP, the desired output will be QR, and then the required input is usual work in. Okay, the refrigerator, the desired output is the RE, or the heat absorption, and the required input is still work in. So based on COPR, okay, so the desired output over required input. So the desired output will be equals to this, and the required input will be based on this, that is your work in. The work in is equals to what? Because according to energy balance, work in plus heat absorption is equals to heat rejected. So if you want to have work in, that means you must have heat rejected minus heat absorption. That means you must take this minus this. So when you simplify, you get something like this. Okay, so that is for your work in. And then you cancel off your S1 minus S4, you will have your COPR as TL over TH minus TL. If let's say, for example, you are referring to heat pump, instead of TL, you use TH. Okay, you can still cancel off the S1 minus S4. So COPR, this thing here will be reduced to this formula here, which is the reverse Carnot cycle. Okay, COP, TL over TH minus TL. And for heat pump, should be TH instead of TL. Okay, and also based on this, we know that in plus in equals to out. Okay, so in plus in, that is work in plus RE, that is the heat absorption or refrigerating effect, will be equals to this. So based on this energy balance, if I were to divide this equation here throughout with work in, okay, throughout by work in, so you will have QR over work in, which is QR over work in, which is the COP HP. And work in over work in should be equals to 1. And this RE over work in would be equals to the COPR. So it will come to this equation here, where you can take COPHP minus COPR is actually equals to 1. COPHP minus COPR is actually equals to 1. Okay? For the reverse Carnot cycle, there are a few limitations, okay, for it to perform as an actual refrigeration cycle. Okay, so this is for a reverse Carnot cycle. So they use a turbine for the isentropic expansion, which is not practical because a turbine need or require a very large floor surface, okay, which makes it impossible as household refrigerator. Second thing is because it is very costly. That means very expensive. Okay, very expensive. In other words, we use the word expensive. Okay, very costly and is uneconomical. So it is advised not to, okay, have a turbine, okay, for the case of any household appliances or household use. Okay, so I have listed down the 2 points here. One is the process 1 to 2. Now, this point 1 here, you can see that is the inlet to the compressor. That is the inlet to the compressor. As I've said, compressor can only deal with single phase, no two phase. Here, point 1, which is inside the dome, means that it is a saturated liquid and vapor mixture, which is also called the wet vapor, which make it impossible for the compressor to function under such a condition. So process 1 to 2 compressor cannot be dealing with a two-phase substance, which involves the compression of liquid vapor mixture. That is the first limitation. The second one is process 4 to 1 here, expansion of high moisture content in a turbine. Okay, it requires large floor area because 3 to 4 here, see, they are using a turbine. Okay, a turbine. So which make it unaffordable for domestic purposes. So therefore, this part 3 to 4 here, and the later section, the modification of reverse Carnot cycle, the turbine will be replaced with something which is economical, or we can say cheaper as compared to the tank, which is called the expansion valve, the thermal expansion valve or throttling valve. Okay, but then using a throttling valve or an expansion valve make this path here 3 to 4 becomes irreversible instead of reversible. So when you look into this TS diagram here, from 1 to 2, 2 to 3, 3 to 4, 4 to 1, the whole cycle is under reversible, internal reversible process. But then if let's say, for example, we replace this turbine here with an expansion valve, the whole thing 3 to 4 becomes an irreversible process. We will deal with that later on. And thank you for this part. Thanks for coming and thanks for listening to my explanation. I hope it does helps. Thank you very much. Bye-bye. Okay, the ideal vapor compression cycle. That's the modification of your reverse Carnot cycle. So due to this few impracticalities of reverse Carnot cycle, that is why we have the ideal vapor compression cycle, which is still not the real actual cycle yet, okay? Now, the ideal vapor compression refrigeration cycle. So the vapor compression refrigeration is most widely used cycle for refrigerators, air conditioners, and heat pumps. So I hope you all know what is the difference between refrigerators and heat pumps by now, okay? So this would be the schematic diagram for the ideal vapor compression refrigeration cycle. So instead of a turbine, we still have these components here: the evaporator, the compressor, the condenser. Okay, but then we replace the turbine, which is in the reverse Carnot cycle, with an expansion valve. Okay, so during the expansion process here, what happens is the liquid or the liquid refrigerant, or the mixture of liquid and vapor refrigerant, will undergo a throttling process, an irreversible throttling process, which will give you equal enthalpy. So H3 is equals to H4 for this part. And this should be a direct valve. I have drawn the wrong symbol. Okay, so you have only the top triangle, you don't have the bottom triangle. Okay, so directional valve. So that means it only allows it to flow from one direction, not reverse. Okay, non-reverse, yeah, only the upper triangle. So flowing from the condenser to maybe the receiver, or to the evaporator. So here they don't show you the receiver. Okay, so during this process, the enthalpy is constant. The same for compressor, condenser, and evaporator. They are still under the condition reversible processes. So it must follow reversible processes must for these three components. The compressor will undergo isentropic compression, reversible isentropic compression. The condenser and the evaporator, they will run at constant pressure, heat rejection here, and constant pressure, heat absorption here. So this would be the TS diagram, which you can now see. You don't have a state point 3 to 4 solid vertical line going down to point 4. Instead, you can see a dashed line, point 3 to 4. A dashed line here represents the irreversible process. Irreversible process. So I have this TS diagram. You can have two different TS diagrams. One is based on dry saturated at point 2, and the other one is based on superheated at state point 2. So that means at state point 2 here, there are two possibilities. Either it is dry saturated or it is superheated. Okay, so I have both of these TS diagram drawn here to show you the difference. Okay, so the first diagram, as you can see, state point 1 to 2 here is isentropic compression. The compressor, the device that is used to perform this job, is a refrigerant compressor. And so that is where you have your work input. Then from state point 2 to 3, this has to be under constant pressure process. That is reversible constant pressure heat rejection in the condenser. So during this, what happens is there will be a changes in phase taking place. You can see here the temperature still remains constant and pressure also constant. So during this constant temperature, what happens is heat is continuously rejected to the environment or to the surroundings. Okay, when it changes is from from vapor back to liquid. That is in the condenser. Then it goes into the expansion valve, which is a directional valve. It undergoes irreversible throttling process or irreversible expansion, where the enthalpy will remain constant. So this is the only part that is irreversible. The rest of the three is they are reversible. So then from state point 4 to 1, what happened is the mixture of liquid and vapor will go into the evaporator, okay, where it will undergo a further changes in phase while temperature is constant. And then when you look at this state point 1 here is still wet vapor, 1 to 2 here, which is not advisable or which cannot be tolerated, because your state point 1 here has the mixture of liquid and vapor, and that will cause the compressor or the refrigerant compressor to burn very fast. So what is the suggestion? What is the suggestion is, okay, so this point 1 here, what we do is we bring it to the point where it touches the dry saturated vapor line, where the compressor inlet here is only 100% dry vapor. Then it will undergo isentropic compression until it touches your condenser pressure at state point 2. So you can compare. Your state point 1, instead of being here, now it is at this point here, is sitting on the dry saturated vapor line. Okay, so state point 1 will be dry saturated at the evaporator outlet and the compressor inlet. And then the state point 2 here is superheated. Okay, so from state point 2 to this point here, my pointer here, the refrigerant undergo desuperheating. Desuperheating, okay, so that means from 2 to this point here, it will undergo a slight change in temperature first, but the pressure is still remain being kept constant. So after reaching this point, it will undergo changes in phase until it is totally changed to liquid. Okay, so that is the exit of the condenser if we don't take subcooling or undercooling into account. That will be the point 3. So, and then the next thing that you need to compare is, if let's say, for example, you compare this vapor compression refrigeration cycle with point 2 as dry saturated, you got to see that when it compares to reverse Carnot cycle, actually your refrigerating effect, that means the area under 4 to 1 is reduced. If let's say your point 4 is somewhere around here, which is particularly below your state point 3. So the area is actually, the area of this is actually reduced. So that means the refrigerating effect or the heat absorption by the refrigerant actually reduced if we change from reverse and introduce to the ideal vapor compression cycle, with state point 2 is dry saturated. But then when you look at the next diagram, the area under state point 4 to 1 actually has been increased. So that means it shows that the heat absorption also is being increased if we use the superheated model. Okay, so these are the few assumptions that we have to make when we consider ideal vapor compression refrigeration cycle. First point, okay, irreversibilities within the evaporator, condenser, and compressor are ignored. So we won't be considering any irreversibilities that is within evaporator, compressor, and condenser for this. Then the next point, no frictional pressure drop is allowed in the evaporator and condenser, and as well as in the compressor as well. Okay, then the third point, refrigerant flows at constant pressure through the two heat exchangers, that is the evaporator and the condenser. So that means in the condenser and the evaporator, as we can see in both TS diagram, it happens at constant pressure. Then the next point is heat losses to the surroundings must be ignored. So we cannot consider there is a slight heat transfer from these two devices. Okay, we assume that that is perfect, or especially in the compressor, we assume it is perfect isentropic. Okay, and the last point is compression process should be in isentropic. Okay, should be undergoing a reversible isentropic process. Okay, then the next thing is, this is your pH diagram for superheating. That is how it is being shown. Okay, this will be your isentropic curve on pressure against enthalpy diagram. This is also a saturation dome. At this point here is also dry saturated vapor. At this point here is still superheated. This is saturated liquid and this is mixture. And this should be dashed line, not solid line actually. So you have heat transfer into the system and heat transfer out of the system, which is the refrigerant, the cooling agent. And this would be your TS diagram, which we have been seeing just now. Okay, so here I think you know each of these process here already by now. 1 to 2 is a reversible adiabatic or isentropic compression of refrigerant. The saturated vapor at state point 1 here causes state point 2 to be superheated, causes state point 2 to be superheated. Okay, so the work in here, work input by the compressor should be H2 minus H1. So your H is here, H2, and your H1 is here in case if you are looking at a pH diagram. Then state point 2 to 3, okay, that is from here to here, okay, or from here to here. So you want to find the amount of heat rejected, you can take H2 minus H3, okay. Then from 3 to 4, which is an irreversible expansion process, and remember the enthalpy should be constant, that means the same. And then 4 to 1, when your desired output is to cool the surface, to cool the surroundings, then you will have to take this. If you were to heat up the surroundings, then you will have to take this, okay, as your desired output. So from 4 to 1 is where you have your evaporator or in the freezing compartment, and the heat absorption or the refrigerating effect is usually taking the H1 here minus the H4 here. Okay, then next, sorry, okay, there's too much okay in my in my explanation. I'm very sorry to this because I have got to used to it. If I stop saying okay, then my explanation will not be that smooth, because maybe this has been my habit, my bad habit. Okay, no, take note of this here. The ideal compression refrigeration cycle is not an internally reversible cycle. The ideal compression refrigeration cycle, that means this whole thing, is not internally reversible cycle. Because of this part here, you have involved a throttling process which is irreversible. So that is why it is not complete reversible. Now, if the expansion valve or the trim device were replaced by an isentropic turbine, the refrigerant would enter the evaporator at state point 4S. Okay, instead of state point 4 as I explained just now. However, replacing the expansion valve by a turbine is not practical due to the means if you want to replace expansion valve with a turbine, is not practical due to the added cost and the complexity. Okay, so this is the important notes and the additional notes why we don't use reverse Carnot cycle for actual, as a model for actual refrigeration cycle. We only use the ideal vapor compression refrigeration cycle as a model. Okay, the COP improved by 2 to 4% for each degree Celsius. The evaporating temperature is raised or the condensing temperature is lowered if you replace by a turbine. Okay. So now, superheat compression cycle, vapor compression, as what I have shown you just now. So can see here, okay, that is your work in heat reject, okay, RE, refrigerating effect. Now we the last one, that is superheat with undercooled vapor compression cycle with undercooled. So you can see state point 3 here. What happens is it goes on this path here, that is your saturated liquid line, down to another point 3A. This is only when it is undercooled. Okay, the reason is also the same, to improve the COP, or sorry, to improve the RE here, the refrigerating effect. So sometimes it is being undercooled. So if I want to find the enthalpy at this point, if let's say the question say it is being undercooled by 5K, so you have to take this temperature here, minus 5 to find out the temperature at 3A, and then from the property table you have to search for the pressure and enthalpy based on this temperature. And then for the expansion process, the irreversible expansion process, which is 3A to 4. So we only equate H3A to H4, not H3 to H4. Please take note when it is undercooled or subcooled. H3A is equals to H4 and is not H3 equals to H4. And why 0.3A is here and not along the pressure line, the condenser pressure line? In actual practice, your 3A should be along the condenser line. But for simplicity and for convenience, okay, we consider 3A should be along the saturated liquid line. So you can easily found it by referring to the property table. That is for the convenience and simplicity. Okay, and remember during this process, H3A would be equals to H4. So this is how, and I've shown you here how to find out the enthalpy at state point 3A. So your heat rejected, okay, should be H2 minus H3A. It's no longer H2 minus H3. Okay, during your irreversible expansion process, H3A equals to H4, not H3 equals to H4 anymore. Please take note of this. Okay. So that's for today's lesson. Thank you. Stay safe and bye-bye. Thank you. See you in the next lesson.